5.3 Polynomial functions. So this lesson's all about different types of polynomial functions, how to name them, how to add things, how to do stuff with polynomial functions. So first, we talked about before when we talk about polynomial function, instead of polynomial just equations, polynomial function should only have one variable, right? It's gonna be y equals this polynomial equation. Right, so it should be one variable, notwithstanding the y. That's like the f of x as a function notation. So within the function, you only have one variable. So that's when you see stuff like this. A key thing to understand is also linear coefficient. Linear coefficient is the coefficient of the highest degree term. So wherever the highest degree term is, which we did earlier in the lesson, earlier in the chapter, then the number in front of that is the linear coefficient. So you see right here, a constant term, well, that's the linear coefficient. A linear term, well, the highest power is right there, so the linear coefficient is 4, the degree is 1, right? 5x squared, 8x cubed. Now it doesn't necessarily have to be in the beginning. They could put it anywhere. If I gave you this, my linear coefficient should be -5 because the highest power is in the middle. Now, proper notation, highest power should be in front, but they don't have to put it that way. Right, so those are all the terms, linear coefficient. Now there's a special type of polynomial function called a power function, where you only have the one term. Like instead of having all that extra fluff, all you have is that one term. So power function, something to the effect of 3x to the 5th, or -2x cubed, right? Those are power functions. There's nothing, it's just all about the power. So that's a special like vocab thing. Anyway, for each one of these, you want to state if it's a polynomial function in one variable, right? If it's a polynomial function, and then what's the linear coefficient. So the first one, well, they're all the same variables, so that works. So it's a polynomial function, and the linear coefficient would be 11. Highest degree is 6. Over here, again, all the same variable, so it's a polynomial function. The linear coefficient is the highest power is -10 because the highest power is 7. -10, and then highest degree is 7. Over here, there's a y there, so no, not a polynomial function. It's a polynomial, it's not a polynomial function. Not poly function. Still a polynomial though. And this one, again, no. So not poly function again. So there's more than one variable. Okay, so there's that. Let's move on. A little review, right? Remember how we enter in values for each function? Right, so if you see a W5, all that means is you're going to plug the 5. We'll do the 5 for this one, do the 4 for the one down there. For all these terms right here. For all the x's, right? So W5 just means -2, 5 to the third, plus 3, so the times 5 minus 12. Forget you do this first. So 125 times -2 plus 15 minus 12. Be -250 plus 3, so -247. Alright, so that's this function notation. Again, and all that means is, so like if I rewrote this, W5 equals -247, it's like a sentence. It's just saying, hey, when you plug in, it's a bad 2. When you plug in 5, you get -247. That's all that means. The answer is -247. It just says, hey, when you sub in 5 into the function, you get -247. And it would have been likewise for this one. I could plug in -4 and get an answer. I'm just going to skip it because it's the same thing. Now let's get a little more interesting here. This is going to get fun. Okay, so we're used to having f and g be functions. In this case, c of x is my function and d of x is my function. They want you to find each one. So they want me to find c of y cubed. Now again, just like up here, when we plugged in 5, right? It doesn't matter what that thing is. That could be a 5, it could be a triangle, it could be 15. Whatever is in that parentheses, you plug in for the x's. Same goes down here, right? In my parentheses here is y cubed. So wherever I have little x, I'm going to plug in y cubed. Because c is just this. C is 4 something cubed minus 5 times something squared plus 2. That's all c is. And whatever is inside the parentheses says plug that in for the parentheses. That's all it works. So in this case, I'm plugging y cubed. Change the color a bit. So I'm plugging y cubed. Remember, power to power we multiply. So 4y9 minus 5y6 plus 2. And that's the answer to that. 8, similar idea. Actually, let me scroll up when I need my function. So similar idea. Now notice there's two parts to this. They have this. Let's deal with this part first. D3z. So same idea. D is 3 something squared plus 6 times something minus 10. That's what D is. We're gonna plug 3z in for all the x's, all the spaces. 3z. Now we're not done. There's also this -4 out here. Well, it does the exact same thing, right? There's a bracket here. There's a -4 on the side. So we're going to multiply all this by -4. So that's the way it's set up. You do the function. Oh, the outside is multiplied by -4, so that gets multiplied on the outside by -4. The rest of it's just simplifying it. So like square both of them, you get 9z squared. That's 18z. This is going to be 27z squared plus 20 times 120, 112, 118, 108, sorry. 108z minus 10. All being multiplied by -4, right? To simplify the inside. You distribute this -4 to everything, and you get 80 plus 28, so -108 also. And then that's going to be plus -4 times that's -432, and then plus 40. So that's all that simplified, right? A lot of work, but it's hopefully not hard work. It's just, okay, plug it in, simplify it, multiply it out. And the same thing goes with this one. This one we'll just set up. We won't actually solve all the way because it's time. Let's look at this part first. I'll just in black. Right, so they don't show it, but there's a bracket here. There's an implied bracket, just like there's one right here. So first I gotta do C of 4a. Now let's see what C is. C is 4x cubed minus 5x squared plus 2. So it's gonna be 4 plus 5 plus 2, if I remember correctly. That's a -5. So we have that, and then we're going to plug in 4a for all of the spaces. And then on the outside, we're going to multiply by 6. So that's that left part. Once I simplify that, I'm good. But that's all the left part. A lot of stuff for the left part. Now let's look at the right-hand side. This part. So again, we're going to do this part first. So D, if you remember what D is, it's that function right there. D is 3 something squared plus 6 times something minus 10. And in this case, what we're plugging in is 3a minus 5. We're plugging that whole binomial function there. So this is going to be 3a minus 5, 3a minus 5. And then we're going to multiply all of this by 2. Right? So that's how you work with functions. Now again, it's ugly. That'd be a lot of work to simplify this. I don't have the time or space to do it, but that's the idea. The hardest part would be right here. The most annoying part, I shouldn't say hardest, is right here. Remember, that is not 9a minus 25. That would be 3a minus 5 times 3a minus 5, also known as 9a squared plus minus 30a plus 25. And then you still multiply by 3, and you still do all that. It's a lot of work, but that's the idea, though. Right? Just work within the functions. Okay, second part and last part of this lesson is how do we talk about functions? What do they all look like? So we're going to talk about how to graph polynomial functions. So first thing I want you to notice, there's a difference here between the degrees. So degree 0, constant term, blah, blah, blah. Degree 1, the linear term, right? Degree 2 is a quadratic function. Degree 3 is a cubic function. Quadratic, we don't care about the names, but notice degree 4 and degree 5. There should be a difference between the even functions and the odd functions. You see it? Difference is even degree function, sorry. Very important. It's about the power. So if it's an even degree function, then if you look at the way it ends, they always end on the same. They're both on the bottom or they're both on top. So even degree function, when we say it's the same, that means it either starts top, ends on top, whatever happens in the middle happens, or they both end on the bottom, whatever happens in the middle happens. So that's an even function. I could right away tell, like looking at it, go, oh, they're both on top, both endpoints are on top or on the bottom, even function. While the odd functions, odd degree functions, even degree functions, again, it's all about the power. Odd degree functions, if the leading power is the odd degree, they switch. Right, look at them. So like that, and like that, and like that, and like that. If it starts on the bottom, then it's end on top, or vice versa. So that's all about the powers, and that's actually what we're talking about next, right? Even degree functions, it's top or bottom, bottom top. So we call that the power rule, degree rule, whatever. But it's an easy way to tell between an even and odd function. Even degree functions match, odd degree functions switch. And while we're here, let's review. Let's talk about zeros, right? Remember, a zero, a real zero, a real root, is the same thing as a zero, which is an x-intercept. If you look at this one, this has 4 real roots. So it's an even function. Over here, and you have 0 real roots, it's still an even function. Over here, you have 3 real roots, odd function. 1 real root, odd function. There's one caveat to that. That is a double root. When you have an even function that bounces, right? You're like, oh, it's only 1, but it happens to be a double root. So only like proviso. But it is a double root, so it does count as 2. So it still works. Anyway, the main thing I want you to take back from this is that an even degree function should either start on bottom or start on top. An odd degree function switches. So even, same, odd switch is the key. So that's an easy way to tell what power it is, how it should kind of look. Next, let's talk about how do we know if it starts on the top, on the right hand side, or if it starts on the bottom of the right hand side. So how do we know that? That's all from the leading coefficient. So we call this a leading coefficient test. So let's look at the leading coefficient right there. If that leading coefficient is positive, then we're going to start on the top right. So we're starting on the right hand side. So it's going to look like this. Right, when we start on the top, we're going to start on the right hand side always. If that leading coefficient is negative, we're going to start on the bottom right. Bottom right. Just like this. So you can tell right away if that function is negative or positive. Just think about when we used to do like negative x squared, right? Like the graph looks like this. That's all you need to know, right? Oh, it's a negative, starts on the bottom right. Oh, it's an even function, so they're the same, bottom left. All stuff like that. So I could tell right away by looking at these that, oh, that's a negative, starts on the bottom, so that's a negative coefficient. It's like a negative 3x cubed or something. And then it's odd because it's switched. That's a negative leading coefficient. These are all positive leading coefficients. Right? Very easy to tell. And actually, before we get to some of that stuff, I'm going to add a little example here. Let's get f of x equals 3x to the 5th plus 4x squared plus 10x minus 1. I want to talk about the end behavior of this graph. I just want to draw a picture of it. So let's draw the end behavior. Well, so first we look at the leading coefficient. It's a positive. So I know it's going to be top right. It's going to look like that. And then I look at the power. It's an odd power. So I know it switches. So it's going to be bottom left. Alright, so that graph's going to look something to that effect. Right? Top right, bottom left because of the way the way the powers works. Actually, let's do another one. I'm gonna scroll down a little bit to get some free space. Let's do a few more. So I like this stuff. Let's do one last one. Let's look at this one. So first thing I want to look at is the leading coefficient. So my leading coefficient is negative. Negative means we're going to start on the bottom right. So bottom right hand side. So my graph's going to look something like this on the right hand side. Next up we look at the power. In this case it's even. Even means you keep it the same. So if it's bottom right, it's going to be bottom left. So again, it's going to be kind of like this. Who knows what goes on in the middle? It might flip, it might do different things, but that's the end behavior. The next one, another negative. So again, it's going to be bottom right. We wish on the right hand side. Well, this time the power is odd. Odd power we switch. That's going to be top left. So again, who knows what happens in the middle, but we just want to know the end behavior. And behavior says, hey, that should be, since on the bottom right, and then it's since it's odd, it's going to switch and in the top left. So that's the end behavior stuff. And let's go on to the last part of stuff we can do today, which is this right here. So for each of these things, I'm going to describe the end behavior. I'm going to determine whether it represents an odd or even degree. I want to state the number of real zeros. Remember, real zeros are x-intercepts. So that's all we got to do for each one. So for A, end behavior is easy. We're just going to write it like this. Bottom left, top right. So you could write this, or you could say, ooh, that's ugly. So you could write like this, hopefully nicer than mine. Oh, that's still not good. Or you could say bottom left, top right. So from that I know, hey, the leading coefficient's positive, and it's an even power. That's the stuff I know from that. B, they want me to say whether even or odd degree. Well, look at, they switch, so it must be an odd degree function. And then C, the number of real zeros. Remember, real zeros are just x-intercepts. This has 3 real zeros. There's 3 x-intercepts. Next one, 12. Again, 1 is end behavior. Bottom left, bottom right. So you could just draw the picture like this. You could say bottom left, bottom right. Either way is fine. B is what degree, is it even or odd? It is an even, so they're the same. And then C is how many real roots. This actually has no real roots. 0 real roots. Okay, last thing. Application problem. A clothing manufacturer profitability can be modeled by P of X equals this, where X is the number of items sold in thousands, and P of X is the company's profit in thousands of dollars. So keep in mind, we always want to know what each thing means, right? P of X is profit in thousands, so that's profit, and X is the number of items they sold. So X is how many things they sold. Use a table of values to catch the function. Yeah, we're going to use a calculator for that. We can do a table of values, I'll just take forever. Determine the zeros of the function. Also, use a calculator for that. So let's bring my calculator out. Always got to turn it on. Let's go here. Let's delete these things. Clear. Clear. There we go. Oops. Clear. Okay, type that in. Negative x to the fourth. Now, the 4th power should be done before it. 4th power, we don't have a button for that, so we can put a caret button. That's any power you want. If you press that, that would be any power you want. And then plus 40x squared. If you're asking why am I using y2, no reason. I didn't realize until right now, so it doesn't matter. Minus 144. We're going to graph it. Now my window's really off right now, so I'm based on something else. So let me zoom in, or put zoom standard, zoom 6. Even then, it's still kind of hard to read. So you have lots of options, right? You could put zoom fit. You could just fix your window. I'm going to fix my window because I don't mind this. I want to see higher and lower and see what it looks like. So I'm just going to fix my y to be like negative 100 to 100. Just to see what that, just to play with it. Let's have some math fun here. So I have a better idea what it looks like. I probably could go higher if I wanted to. I could probably go like negative 150 or something. To 150 and see how that works. Right, I was fine with the x values. I need more y. Oh, it's not good enough. I think I'm good enough. Right, I could tell what it looks like. I'm doing oh, that's a bad graph. It looks like kind of like this. Is that the right idea? Nope, upside down. Yeah, I suck. Let me first make a nice line. I'll use the thing. I wish we could use this. And I think I say that every single time also. Let's get used to it. Come on. Come on. There we go. Let's move it to like here. Or not, you know. It's fine the word. Okay, whatever. Anyway, the graph. So I'm getting it wrong again. So down, up. Okay. It's a look at negative coefficient and even. Right? I should have known that from there, right? It starts on the bottom right. It's even, so it ends on the top right. Ends on the bottom right also. Ooh, not the best graph. I didn't mean to go that low, but there we go. So we have that. Determine the zeros of the function. Remember the way we find zeros on our calculator? We're going to put second calculator 0. And all we gotta do is get close to one of them. And go a little left of it, a little right of it. And I get 2. And then we'll find the other one the same way. Find the other one the same way. I just did it so we don't have to worry about it. Don't forget, let's label this. X is the number of items sold. And thousands. And P is profits. Okay, so A and B are done. Check and check. So my zeros of the function are -6, -2, 2, and 6. Now let's look at C. Between what two values should the company sell in order to be profitable? Well, this is profit, right? So we want a profit to be positive. So between here and between here. But does this actually make sense? Could I sell -2 to -6 shirts? Not really. So I don't really care about this. Between 2,000 and 6,000 shirts. So let's see. And then do you explain why only 2 zeros are considered? Because you can't sell negative shirts. I'm not sure what negative items. Sorry, I can't sell negative items. There we go. That's the lesson.